Just in time. Your laptop's shut, folks. Your name tag's out. As the semester progresses, the number of people in the classroom seems to keep decreasing. At some point, I'll begin passing out, a sign-up sheet. So based on poll, the poll responses from the past few lectures, it seems like almost 40% of the students don't bother to watch the lectures. So they're going to lose that point for attendance, but beyond that, you're kind of missing the point, right? So this is a standard spiel I make every semester, and some people kind of mock me for it, but you pay $7,000 a year for every course. So how much is that per lecture? At 26 lectures. That's about $2,500 or $250 a lecture, right? So if you're from India or China, that was your grandfather's annual salary. Stop and think about it, right? And if you're from one of the other impoverished parts of the world, it was more than your grandfather's annual salary. So every time you bounce a lecture, you're slapping your granddad. That's literally what you're doing. You're insulting him. You're saying 1 year of your work was not worth the inconvenience I had to get to class. You have to be more respectful of the money you pay and actually come to class. Even if I am boring, if I'm killing you and I'm putting you to sleep, you have paid for it. You should be here. You should be demanding that I do a better job, not bouncing off. Because when you do that, you're humiliating a whole lot of people and you don't know it. Mostly yourself. Right? So anyway, let's begin. We're going to start with, continue with convolutional neural networks. Does anybody remember what a receptive field is? No?
It's a window size.
Not quite. So it was, Vegan? Does anybody want to tell me what a receptive field is, Giovanni?
Isn't it the kind of pattern of features that the window is recognizing?
So we actually had this information in the slides. I asked you to go back and look, remember? So go back to your granddad and and how much he earned every year. You're supposed to go and check this stuff out. So I'm not going to give you the answer. Go back and look at the slides. There were 10 slides. It's not too much effort to go just glance through them and get an idea of what we are talking about. And you should know what I'm speaking about when I speak of a receptive field, right? Can you shut your laptop? Again, thank you. Be respectful, not just to me, but to everybody who doesn't make $350 in a year. So why is the closed caption showing up on the screen? That's a good one. Can we get rid of that? Any idea? All right. You're going to please ignore whatever is showing up on the screen. Now, we're going to continue with CNNs. But first, we begin talking about cats. So for the longest time, people wondered how humans perceived visually. How did you make sense of the world that you saw? How do you see, right? What is the neural process from the light received by the eye all the way back to recognition? And much of early research was based on behavioral responses. How do you compose patterns? So for example, the figure to the top left, what does that look like to you? Is it really a cube? Right? It's just a bunch of Pac-Man-like figures, right? What about the second one? You've built up the dog in your head. It's just a bunch of bizarre patches. or that panda. The one to the extreme right is my favorite. What do you see? It's a spiky sphere. There is no sphere at all. There isn't even the faintest hint of a sphere. The spikes are there. You imagine the sphere. So this was what they call Gestalt, where the human brain sort of composes things and you imagine you're seeing things based on very partial information. And in fact, so this is the truth, much of what you see you never really saw. You just imagined it. In fact, I may not be here. You're just imagining me, right? Anyway, so the way people sort of try to analyze how we sort of perform this business of visually recognizing the world was to study the behavioral responses, Gestalt, how do we compose patterns, what kind of patterns do we actually detect. But this doesn't tell us about the underlying neural processes itself. For that, we had to wait for these two guys, Hubel and Wiesel, in 1959, who they performed this first study on the neural correlates of vision in this paper they titled Receptive Fields in a Cat's Striate Cortex. The cat's striate cortex, now the human eye and the human visual system is a classic example of why we are not intelligent design. If anything, we are very unintelligent design. Firstly, your eye has this bizarre characteristic where the nerves that actually conduct the signals are in front of the retina. So they've got to fold back and punch a hole through your retina to go back into the brain, which is why you have a blind spot. In fact, there are very few animals which have the eye done right. The octopus is one of those where the nerves are behind the retina. So, but then if you were to be designing a system of this kind, the physical hardware, you almost certainly would design it such that the portion of the hardware that began the processing the signal was the one that's closest to where the signal is received. That's not what happens in our head. That goes back all the way to the back of your head. And that's where the initial responses happen. And then those responses accumulate and they go forward back through your head and they come to your forebrain before you begin actually interpreting what you see. So this portion of the head at the very back where the signals are first registered is the V1 portion of the human brain. And the equivalent part of the cat brain is what is called the striate cortex. It's out at the back. And the neurons are striated, which is why it's called a striate cortex. And so these two guys got 24 cats, and they anesthetized them with truth serum, and they stuck electrodes into individual cells of the brain to study their responses. And then, because these were anesthetized, they just tied them up, they opened up their iris, and they beamed light in different patterns to see how these cells responded. They beamed light in different patterns, circular patterns, linear patterns, whatever, and had different wavelengths, and try to figure out what actually made neurons fire. And here's what they found. They found that each neuron in the brain responded to a small portion of, to signals in a small portion of the retina. And so they specifically had this kind of response where there were portions of firstly, the restricted retinal areas on which the illumination influenced the firing of a single neuron was called the receptive field. So go back and look at the slides. You have the computational equivalent even for convolutional neural networks. But within the receptive field, they found two kinds of responses. There were regions where if light fell on it, the neuron responded. So these were the excitatory regions. There were other regions where if the light fell on it, the neuron explicitly did not respond regardless of what was happening elsewhere. And then there were other regions where the absence or presence of light made no difference to the response of the neuron. So a typical neuron might have a response like this, where it responds positively to any light in this region, negatively to responses in these red regions, and does not respond to anything elsewhere. And so what they found was that the receptive fields of these neurons were basically kind of linear in pattern, but they could be oriented any which way, horizontally, vertically, whatever. And firstly, if you just flashed a light all over the eye, the positive and negative portions of the receptor field canceled each other out, so there was no response. You needed to have very specific patterns falling on the eye. And then you might have a neuron which responds only to, this is from a monkey, these are from mice. You might have a neuron which only responds to linear patterns of this kind, which means there must be a line and there must be no other signal on either side of the line. So the line kind of stands out. And so here's one of their pictures where they actually take a light and then just move it back and forth in different directions. And you can see how the neuron fires. When the light is moving in a horizontal direction, there's no firing. As the light rotates, when it becomes vertical, the neuron really fires. But then if it continues to rotate and becomes horizontal again, it stops firing. So these are neurons which respond to vertically oriented patterns of light. So oriented slits of light were the most effective stimuli for activating the striate cortex neurons. But then they found more. They did later studies, and they found that within the striate cortex, there were actually 2 levels of processing. And they call these 2 levels of processing S cells and C cells. So the S cell responded to patterns, and the C cells cleaned up the pattern. How does that happen? This picture kind of explains it. So in the retina, each cell responds to some kind of a circular pattern. But the S cell in the brain responds to a union of a combination of retinal cells which are arranged somewhat in a line. And so if you have patterns in linear patterns of light, this S cell might fire. But then because your retina is so sensitive to light, it can detect individual photons, there's going to be a lot of noise. And so to clean it up, you had a collection of these S cells that sort of fed into a C cell, and the C cell responded to the strongest response of any of the S cells that it was connected to. So in some sense, the S cells detected patterns, but the C cells cleaned up the noise. So the complex C cells basically build up from similarly oriented S cells. You have many S cells which are all looking at maybe a light pattern in this direction at a specific location. A bunch of those go into a C cell, which cleans up their responses so that you get somewhat less noise sensitive response. And then at the next level, they find that the next level of processing is a bunch of C cells which connect to S cells again, which connect to a bunch of C cells. And so as you went through the brain going forward from V1 to V2 to V3, these patterns built up where each layer of neurons operated on the output of the previous layer of neurons. And so they showed a complex buildup, building more complex patterns by composing early neural responses. And they spent a lifetime working on this. They wrote several papers, and through the papers, they kept showing that this really was kind of how the human visual system worked, or the mammalian visual system worked. That you started off with simple, almost linear receptors, which again had 2 components, the sensors and the cleaners, so the S cells, which sense the pattern, and the C cells, which clean them up. And then you had layers of these, where each layer built up on the response of the previous layer. And so as you went through the layers, the patterns became more and more complex. Now, all of this was very fine, but at some point they stopped working on cats. They started working on monkeys, so you stop reading the papers. But to add insult to injury, they also finally found that maybe this wasn't everything, right? This model cannot accommodate color, spatial frequency, and many other features to which neurons are tuned. The exact organization of all these cortical columns within V1 remains a hot topic of current research, and this hasn't changed a whole lot since then. Anyway, here's your first spot. Give them 30 seconds of one question, 45 after. This is an easy one. Okay, Time's up. Can someone on Zoom answer? Which is correct?
First one.
First one. You guys agree? Yeah, right. So that was the basic idea, right? So S cells find patterns and C cells clean them up. So that's where things stayed, 1959. And there were some subsequent biological studies afterwards. But we didn't actually come up with a computational model till this guy Fukushima started working on it. And so we have this model, which he called the Neocognitron. He tried to computationalize the Hubel and Wiesel model. And in the process of computationalizing it, he found that it didn't explain one particular thing. How many of you have heard of the Jennifer Aniston neuron? Someone, yes. What was it?
It was a neuron that they were able to find in the brain that responded only when showing photos of a particular celebrity's face.
Yep. So people who have epilepsy, turns out, are great for brain researchers. These guys spend time in the hospital with their skull opened up while the doctors try to fix the lesions. So the researchers go there and stick a whole bunch of electrodes in the brain, a mesh of electrodes, and then make them guinea pigs. So there was this one study where they showed this person all kinds of pictures, and they found that there was one specific neuron in the person's brain that only fired when it was shown pictures of Jennifer Aniston, when the person was shown pictures of Jennifer Aniston. So that's the Jennifer Aniston neuron. There was a paper in Nature about it. But more generally, we actually have neurons which could maybe respond anytime you see your grandmother. So the point is, you're going to get a response to seeing your grandmother, but it doesn't matter whether the grandmother is in the center of the frame or off to the right. If grandma comes into the picture, the neuron will fire. You recognize grandma. So this grandmother cell fires regardless of the location of grandma. And this was something that the Hubel and Wiesel model didn't actually capture. So Fukushima came up with a computational model, which not only computationalized Hubel and Wiesel's model, but also introduced this notion of positional invariance. And he called this the Neocognitron. Clearly, if the name of the model is the Neocognitron, they must have been an older cognitron, so I assume this was version 2. But here's the model. He said that the visual system consists of a hierarchy of modules, where each module in turn has two components, a bunch of S cells and a bunch of C cells, just like Hubel and Wiesel said. S cells respond to the signal in the previous layer, and C cells confirm the S cells response. Of these two, only S cells behavior is learned. This behavior of C cells is determined simply by their structure as determined at birth. It never changes. And so furthermore, you wanted to have position invariance. So the way he did it, so the way his model was designed, where is a chart? He said that within a SC block, any single SC block, you had several planes of S cells. So we had this block which had an S followed by a C in the original picture. If you looked at this one S, in his model, the S cells were arranged in several planes of this kind. And within each plane, you had many cells, all of which had exactly the same response. The only thing that, only way they differed is in which portion of the input they were looking at. So if you had an image going in, this cell may look at this region. This cell may look at this region, and so on. So each cell looked at a slightly different region, but responded in exactly the same way. Similarly, in the second plane, you would have a bunch of cells, each of them looking at a different portion of the input, but all of them with the same response. The response of the cells in this plane is different from the response of the cells in this plane. So this was the plane of S cells. Then subsequently, corresponding to every S plane, you had a C plane, where you had a bunch of C cells, where each C cell just looked at a small region in the corresponding S plane. And the C cells were small, the C planes were smaller than the S planes because you were using confirmatory responses. So this was one SC block. But then when you went to the next SC block, so this was your first block, Then when you went to the next SC block, you would have, again, a bunch of S-planes. Pardon me. And if you looked at any particular cell over here, now this S cell would respond to patterns found in the same region of all the C-planes. Or the patterns were detected by looking at the responses of all the C-planes in the previous layer in the same location. So each S-plane is, in Fukushima's original work, the S and C cells, the region they each look at was elliptical in shape. So here's how the complete network would look. You would have the retina. You would have the first set of S-planes, where, again, each plane consists of a bunch of cells with identical responses. Then corresponding to each S-plane, you would have a C-plane. So you'd have a collection of C-planes, where these have confirmatory responses, which clean up the responses in the S-plane. Then in the next block, each S-plane is going to look at the same region in all of the C-planes of the previous layer simultaneously, and then respond. And then again, all the cells within any particular S-plane have identical responses. The only difference is where they are looking. And then each S-plane again is followed by a C-plane, which has confirmatory responses. So the C-planes are always smaller than the S-planes. They're grouping things together. And he also came up with formulae for these. How does it respond? So if you actually look at this guy here, this cell over here is looking at a collection of values in this plane, a similar collection of values here, and a similar collection of values here. So whatever is being computed here is a function of all of these values. And so he wrote the function on top is the function that he proposed. Then similarly, when you come to the subsequent C-plane, this C-plane is only looking at a small region of the corresponding S-plane. C-planes look at only one plane, right? And so there too you have the response as a function of all of the inputs to each location. And he came up with he proposed a function that's given down there. And these were based on biological principles. But if you look really closely at them, the first one looks like a ReLU, and the second one looks more like something very similar to a max. And so you can actually write code for it, right? Now, one of the things that happens is that as you go through the cells, in the first S-plane would be big, and it's looking at the entire input image. Then the C-plane is smaller because it's confirmatory. Then the next S-plane is not going to be larger than the C-plane itself because it's basically responding to the C-plane. And then the subsequent C-plane is going to be smaller than the S-plane. So as you go through the layers, each of the planes keeps getting smaller. To compensate for it, the number of planes increases because you don't want to lose information, right? And so at the deeper layers, you're going to get smaller planes, but there's something else that's happening here that's interesting. Where did I leave the chalk? Does anybody? Thank you. So if this cell looks at this region of the input over here, let's say, so the corresponding cell over here would also be looking, say, at the same region of the input, right? Then when you come here, this one is looking at a region of the previous C-plane. So that's going to correspond to a larger region of the input. So the receptive field of this cell is a small region. The receptive field is the region of the input, effective region of the input that the cell is looking at, right? The receptive field of this cell is going to be larger because it's looking at a group of C cells. So as you keep going through the network, the receptive fields of the cells keeps increasing. And the kind of patterns that each of the cells detects is also going to get more complex. In the first layer, maybe they're detecting somewhat line-like patterns, but then as you go through it, it becomes more and more complex. He also came up with a mechanism for training the network. And it was fully unsupervised. Again, it's biologically motivated, right? So how do you think the mammalian visual system learns? There is really no feedback, or at least that was the assumption back then. So I am so sorry, something in my throat. The way he did it was this. So consider that you have some input in some plane. This is being viewed by the same location in each of the different planes, right? So he would find out which of these had the largest response. If this had the largest response, then this weight would be incremented using the Hebbian rule. But this and only this weight, these weights would not get incremented. So only the largest response got pegged. But then once you incremented the weight, the corresponding weight of all of the cells in that plane would also be incremented because they're all identical in response. So eventually, if you go across the plane image, every cell in every plane is going to get updated. So here is the kind of behavior he found. If you just gave the network a collection of images and just let it learn, just let it update the weights using the Hebbian rule with no further signal, then you found that the cells in the lowest layers learned simple patterns like the curves of the A or the horizontal bar. And then as you went through the network, the patterns got more and more complex. By the time you got to the last layer, the individual cells in the last layer began firing. Sorry. The individual cells began firing in response to complex patterns. So here's what he found. When he tried to train a network on collections of images, he found that by the time you got to the last layer, each cell was responding to actual digit-like images. So you might have cells which recognized all, which responded to the digit 0. And these would be quite robust to noise and position and all kinds of distortion. So it was a fairly robust response detection of the digit 0. Some other cell might respond to the digit 1. So you effectively ended up having unsupervised, supervised, but semantically meaningful clustering. So far so good, right? Let's pause it. This is easy. Okay. Yes.
Do you have a way to decrease weights as well? Because that was the problem with the Hebbian rule.
I don't remember, but I don't think he did. But I may be wrong, right? So we'll have to check. I don't remember that specific detail. Okay, time's up. First question. Yes or no? Second. Also true? Okay. Let's see. Yeah. So how did you answer true? Yeah, so how would you add supervision to Fukushima's model? So back propagation from what?
Just classify the
Yeah, but you just have a collection of planes coming out, right?
vectorize it like static and then put it into classify.
Thank you, right? So what you can do is add an additional layer which just performs supervision. That's a simple next step, right? So the Neocognitron is fully unsupervised. Semantic labels are automatically learned. Question is, can we add external supervision? Various people looked at it, and there were many proposals. In fact, the first one was here at CMU by Kevin Lang. And Kevin Lang worked on speech. Jan LeCun worked on images. Jan's work became far more famous. So the idea is this. I can just take all of the outputs of the final layer, final C layer, and then pass them collectively through a decision model, which could be a single softmax or an MLP or what have you, and it's going to create an output. And now I can actually, now I have actual classification, and now I can just have label data and I can train my model, right? So it's a simple extension from Fukushima's model to Fukushima's unsupervised model to a supervised version of the same model. So this is how we do it. You add an extra decision layer after the final C layer. Now we have a fully feed-forward MLP with shared parameters because within each plane, all of the parameters are the same. And because all the S cells have the same weight. And then you can train this using backpropagation, keeping in mind that the C cells are not going to get updated, only the S cells get learned. So now, in the original Neocognitron, basically you had an entire plane and you had many copies of the cell. Instead, you can replace that by having one cell which just scans the image and the response is exactly the same, nothing changes, right? Instead of having many physical copies of a unit, have one copy of a unit which scans and the output is the same. So this is basically what Jan LeCun did. Furthermore, now in the original Fukushima model, every cell had an elliptical receptor field. That's mathematically difficult to deal with. So Jan changed it to a rectangular receptor field. So each of these guys would be looking at a rectangular region of the cells of the planes in the previous layer. So the receptor field of the S cells in the Lth layer would be some KL cross KL. The receptor fields of the C cells is going to be some other square, and the C cells are looking at the S cells, right? So here is what, once you begin writing math for this is easy. Here is what would happen. So if I had a bunch of C cells, C planes from the previous layer, then in this layer, an S cell would look at a small window, a rectangular window of all of the C planes in the previous layer. Corresponding to every position here, there would be a weight, right? This entire region is going to have a weight. And so the computation that you'd perform, we'd first compute an affine function of all of these guys. So you'd be summing over all the planes. Within the plane, you'd be summing over the entire rectangle. And you'd be computing a product of the current value of the plane and the weight. So in this equation, this guy, these two terms are summing over the rectangular receptor field from the previous plane. And this one is summing over all of the planes. So that's the affine term that's being computed. And then you apply an activation function to it. So that's what the S cell units were doing. What about the C cell units? Now, the C cell units are only going to be looking at one plane. So if you have a C plane, this one is looking at just this small region. And specifically, it's going to pick the largest response within that region for cleaning up. So the math is much more simplified compared to what Fukushima had. So this is equivalent to convolving. The first operation is equivalent to convolving. And the second is just a max, right? And then you, of course, have the final supervised, this final classification layer, and then you can train it. So this was Jan LeCun's model way back when in the late 80s. And back then, one of the big problems that we had was recognizing digits. The US Postal Services got millions of letters every day. They were looking for an automated machine to recognize the addresses. So this was something they went to AT&T Bell Labs with. And Jan was in AT&T. And his demo actually shows his system sliding over the letter and recognizing every digit as it comes by. Became very popular. That was LayNet. So the story so far, the mammalian visual cortex consists of S cells which capture oriented visual patterns and C cells which perform majority vote over groups of S cells. The Neocognitron emulates this behavior with planar banks of S and C cells with identical response to enable shift invariance. Only the S cells are learned. C cells perform the equivalent of a max over a group of S cells for robustness. Unsupervised learning results in learning useful patterns, but LeCun's LayNet added external supervision to the Neocognitron, where the S planes of cells were modeled by a scan, a convolution over image planes by a single neuron. And the C planes are emulated by cells that perform a max over groups of S cell units. And that, like second one, actually gives us your convolutional neural network. So we're sort of revisiting what we spoke of in the last class, but from the biological perspective. This is where convolutional neural networks originally came from. They weren't thinking of it as scanning with an MLP, but it turns out that's exactly what they're doing, right? So here's what the CNN looks like. A convolutional network comprises convolutional and pooling layers. convolution layers have neurons that scan their input for patterns, and then pooling layers perform max operations on groups of outputs from the conv layers. And the two may occur in any sequence, but typically they alternate. So you can have a conv layer followed by a pooling layer, followed by a conv layer. You can have multiple conv layers followed by a pooling layer. What you wouldn't have is multiple pooling layers in a sequence because that can be collapsed. So only the convolutional layers and the final MLP. So the output of the final layer of these final set of planes is flattened and sent through an MLP. So only the convolutional layers and the final MLP are learnable. The rest of them are not learnable. So what does a convolution layer look like? A convolution layer comprises a sequence of maps corresponding to the S-planes in the Neocognitron. They're variously called feature maps or activation maps. And here's how the computation is performed. If I look at, so if say this was the layer of C planes from the previous layer, the previous layer C planes, right? And if I come to an S plane, how would say all of the responses in this first S plane of this layer be computed? To see that, you're going, every single cell over here responds to all of the C planes in the previous layer simultaneously, or all of the planes in the previous layer simultaneously, right? So, and the response happens in two steps. First, you compute an affine function of regions of the previous plane, as we saw in the equation way back here. First, you compute an affine function. And then, point-wise, that affine function is put through an activation function. So the affine map is computed by looking at all of the planes in the previous layer. The activation function itself is pointwise. So let's look at how the activation, the affine map is computed first. This is pre-activation. Now, each affine map over here is actually computed from all of the planes of the previous layer, right? So you have to understand how it's computed, you'd have to see how each of the planes in the previous layer contributes to it. So let's just consider the first plane. Let's see the contribution of the brown plane in the L-1th layer to the yellow plane in the Lth layer. Now, I'll call it a map. So this green picture over here is going to be, represents the brown plane over there. Now, as we saw, if I draw things differently, if these were the planes in the previous layer, in order to compute the response at any one point, you're going to be looking at a rectangular region of all of these guys, right? So the way you would look at the rectangular region over here is that corresponding to each position, there would be a weight. So this pattern of weights is what we often call a filter. If you go back and look at last lecture, we call it a filter. So let's say the picture to the green picture to the left shows you this entire plane, and the yellow picture shows you just the pattern of weights that you're going to apply. Now, when you're computing an affine value, there's also a bias, so you must never forget the bias. For now, let's assume that the bias is 0. So the values that you have in these squares represent the values of the at the plane in the previous layer. So all the values here are given by the numbers over there. They're all binary in my example. And so also the values in the little orange square, that represents the set of weights. And in my example, the weights are binary. They don't have to be binary. This is just for visualization. So the way you would do it, you would just place this filter right on top of the top left corner. And then, so the filter values are shown in red, and the black shows the actual map values underneath. And at each position, you're going to multiply the filter value with the corresponding map value. And then you sum them up. And so here, if you sum it up, it's going to be 1 times 1 plus 1 times 0 plus 1 times 1 and so on. That sum is 4. That's going to be the value in the first position, right? And then you would slide forward. And at each position, you would repeat this operation. Let's see what happened. And if you repeated this, you would actually get this set of affine values at each location. I mean, is this operation Clear to you guys? How we're doing it? You know, it's very simple. I stole this picture from the web somewhere, but it's very nice. So, but in fact, you're not looking at just one map, right? You're looking at many maps in the previous layer all at once. So in order to compute this one response over here, you don't just have this one filter here. You're going to have a filter corresponding to this plane. You're going to have a filter corresponding to this plane, another filter corresponding to this plane, and they'll all be different. And so what you would have is something like this. You'd have an entire, as many filter planes as you have planes in the previous layer. So this is the input layer with all of its maps. And you're going to have as many planes, which are also called channels in standard terminology these days, as many channels to the filter as the input channels themselves. And these channels are all going to be different. They're all different sets of weights. And so you'd place the entire collection of filters on the top left corner of all of the planes like so. Perform a pointwise multiplication and sum them up, yes?
We still only need one bias term, right?
Yeah, you only need one bias term, right? Because you're computing one affine value at the end. And then for the next position, you'd slide the entire lot up forward by one step. And then and again forward, and so on. And so this is how you'd compute the entire set of affine values. So at each location, you'd be going over all of the planes, and within each plane, you're going over the entire square and performing a pointwise computed product. So this is the filter value, and this is the corresponding image value at the input location. So when you're computing the value at, say, the location ij, the filter is placed starting from location ij, right? And so the image indices are, the filter indices are k and l, but the images indices are I plus L minus 1 and j plus k minus 1. This is to say that it's starting from ij, right? This is going to give you just one plane. But then you're going to have many such planes in the next layer. So the second plane would have a completely different set of filters. And those filters are going to be placed on the image, and you'll be performing the same scan as before. So if you want k output channels, you're going to have as many filters as the number of channels, but each filter in turn has as many channels as the number of input channels or planes, right? Yeah. Your Denise?
Professor, I'm I guess a bit confused about the previous part. Just to clarify, each filter acts on every single channel inside the input image.
Exactly.
And that forces each of our filters to be essentially size channel, comma, KL, where KL represents.
Correct.
Okay.
KL, I mean, this number of channels times width times height.
Mm-hmm.
Yeah. Yes.
So for the output map, you said we could have that 1 times the number of channels that we have in the output map. What is that represented in like an image? Like what would the output map be for an image?
So I'm not sure I understand the question.
So like if you have the image of a cat, for example, the image of a flower, what would the output map, like what does that represent?
So that's going to represent a specific, so each filter is basically looking at searching for a specific pattern, right? And so this pattern, to detect if the pattern has happened, you're going to be looking at all of the input maps simultaneously. So the filter might be just looking for, the outline of a petal, for instance. And so you're looking at all of these guys simultaneously, and at each position, you're just determining if that pattern has happened or not. That's about it. Yeah.
Professor, why did we have a generic MLP stuck in the end of convolutions? Why can't we just have stacks of convolution going to one, maybe a classifier in the end?
That's what they call an on-call convolutional network these days. Yes, that's a good question, and that's what we indeed do. So there, we like to add complexity just to hope, just in the hope that it's going to work better. But that's it. So now there's a different. So is this whole thing clear so far? Any questions? Yeah.
I just want to clarify for each filter, is it the same filter that we're convolving over all these input layers? Or could each filter, because it's three-dimensional?
So look at the colors, right? The colors indicate the actual set of values.
Okay, so it could be different.
They will be, yeah, they can be different. I've actually color coded it and I've been careful about making sure that they don't convey the wrong idea.
Thank you.
Yeah.
And just to clarify, the number of, like each filter would have its own bias.
Yes. Because it's an affine function, right? Yeah. Anything else? Okay. So here's a different way of looking at it. Instead of looking at it as many different planes, one below the other, which becomes visually a bit tedious, it's kind of convenient to just say, I'm going to stack all of these planes one on top of the other in the form of a cube. So here I have, at least 3 planes. If I stack them one on top of the other, it would be like a cube of this kind, which is 3 layers deep, right? So I can stack all of the kth layer maps in this manner. And now the filter is going to also, just as the filter had one little plane per channel, input channel, if I stack them up, the filter too is going to have, is now going to look like this cuboid with as many planes as input channels. And so now I can rethink the computation in this manner, that at each position, I'm just placing the filter on this cuboid, performing a pointwise product, right? So the formulae don't change at all. Within each plane, you're doing a pointwise product of the filter weight and the plane value. But then finally, you're summing across all planes. And then when that entire summation has been done, you can add an extra final bias term, and that's going to give you the affine value. And so the actual scanning. So this is the first one. That's the product over the inner product over one map. And then you're summing across all the maps. And that gives you the affine value, right? And then you can actually do the scanning by, compute the entire affine plane by scanning this cuboid. So it's a different visualization, but it's less taxing than trying to keep track of many planes all being processed simultaneously, right? So this is how it's usually presented. Now, there are some engineering criteria. The size of the output depends on various factors. It depends on the size of the input. It depends on the size of the filter, and may not be identical to the size of the input itself. So let's take a brief look at this for completeness sake. Let's say I have this input, which is 5 cross 5, and my filter is 3 cross 3. And I don't let my filter go past the edge. What is the size of the output going to be? It's going to be 3 cross 3, right? So because once you get 3 steps deep, you run out of input. And so the size of the output is kind of proportional to the size of the input, but it's losing some columns and rows. How many columns and rows will it lose? 2. So in general, if my input is, say, n cross n, this is n, and if my filter is, say, k cross k, right? The first time I place my filter over here, I'm going to take up k of these guys. So that gives me my first 1, right? But the number of times I can move ahead is simply going to be n minus k. That's how many remain. So the output size is going to be 1 plus n minus k in each side. You're losing, whatever the filter width is, you're losing that minus 1 rows, and the height of the filter, whatever it is, you're losing that minus 1 columns. So if your filter is m cross m and the input size is n cross n, then obviously the output is going to be, what was it? So it's going to be n plus 1, n minus n plus 1 on each side, right? So this results in a reduction in the size of the output. So suppose you don't want the output size to reduce, what would you do? You can say, you know how many rows you're going to lose, you know how many columns you're going to lose. So you can say, my filter is 3 wide, so I'm going to lose 2 rows. So I'm going to pad my input with 1 row of zeros or 1 column of zeros on either side symmetrically. and now the output is going to be the same size as the input. So this is something you do only if you're insistent that the size of the output doesn't change or stays proportional to the input. Now, this convolution operation results in an affine map, and then once you get an affine map, the next step is to perform a pointwise activation, compute a pointwise activation to get an activation map. And so that is simply by applying an activation to every entry in the map. So the overall code, if you looked at it, is going to look something like this. It's going to be, you're going through the layers, right? And at each layer, you're going to get some, you're going over each position, and at each position, you're getting a little segment of the input out. But the segment is going to be width times height times depth, where depth is the number of channels. And your filter is also going to be width times height times depth. And that is the inner product that you'd actually compute. And then, so this would be a tensor inner product because it's 3 dimensions cross 3 dimensions in this example, right? And then finally, and that's going to give you a scalar output. And then you apply an activation to it. So in summary, convolutional layers scan the input using a bank of filters, where a filter is just a neuron in a scanning layer. Each filter jointly scans the maps in the previous layer to produce an output map. So you get as many output maps as filters, regardless of the number of input maps. So again, it doesn't matter how many input maps, right? You get 1 output map per filter. So this is the key bit. And you may have to pad the edges of the input to ensure that the outputs have the same size as the input maps. There's one more component to it. There were these pooling layers. What are these pooling layers? These are something like this. Pooling layers are meant to account for small jitter in the input. So typically, you want to say if there's a flower of petal followed by a sepal, maybe there's a flower. But you don't want to be too concerned about, if there's a small jitter in the position of the petal, does it suddenly stop being a flower? It doesn't, right? And so you want to introduce that kind of position invariance, jitter invariance. The way you would do it is, you'd say if I detect a jitter anywhere in this region, a petal anywhere in this region, I'm going to declare that a petal has been found. How do you do this? The same concept that we applied earlier, right? If the petal detector fires at any of these locations, you want to detect a petal. That's like taking the max. And so within each region, you would be taking a max. Max pooling selects the largest from the pool of elements. So here, for example, if you're looking at the top left corner, and you are looking at those 4 elements, and there were 3, 1, 4, and 6, the largest value is 6. So you just pick the 6. And then you'd slide over to the next position. And here, let's say the 4 values are 1, 6, 3, and 5. The largest value is 6. So you pick 6 again. I'm going to assume that when you're scanning for the map, for the max, you're scanning, unlike in the original model, for mathematical simplicity, it's always convenient to assume that you're always scanning 1 step at a time. So you scan something, you look at a window, then it take a 1 pixel step, and then perform your operation, and take another 1 pixel step and perform the operation. So I'm going to assume that you're stepping 1 step at a time, a stride of 1. And so here the next output would be 6. And then you'd slide forward, you'd pick the largest value, and you do that going top to bottom until you've scanned the entire image. And at each location, you would pick the largest value. Now, typically, when you perform max pooling, you're not going to pad with zeros, because zeros can basically end up confusing you at the edges, right? So max pooling will almost always reduce the size of the input. Now, for mathematical convenience, it's always convenient to think of scanning or convolutions happening with a stride of 1, meaning after you processed an input, you're going to take a stride of exactly 1 pixel. In practice, that's not what we do, but we'll deal with that shortly, right? So here's what max pooling does. Max pooling is not considering all of the layers, right? Each max pooling operation is only being performed on, so a C plane only looks at the corresponding S plane. So max pooling is performed separately for every map. You're not combining multiple maps. But then observe something, I'm keeping track of the position where the max happened. So when I'm looking at a window, I'm going to say, okay, the largest value was at the 2, 2 position. So I keep track of the 2, 2, And then at the output, I'm just going to read the value at the 2, 2 position. Now, this two-step process is going to be important when you're performing back propagation. Instead of simply directly reading the max, keeping track of the location will end up being important. You can have other kinds of pooling, something called mean pooling, where you just take the mean of the elements. This too gives you some degree of jitter and variance. And so here you'll be computing within each position. Earlier, you were picking the index of the largest value and then reading that out. So you're basically picking the largest value. In mean pooling, you just be reading the mean, yes.
So why did you say that we don't usually apply padding when we are using this kind of tool?
Because if you got, say, all negative values for whatever reason, right? You're just going to, if you're performing max pooling, you're just going to read the zeros. You lose information at the edges.
Okay.
So you don't want to, right? So the extra stuff that you get is going to be noise. So you can also have other kinds of pooling. Some people like to have experimented with computing P norms, or even throwing an entire neural network in here instead of pooling. Yeah.
Could you elaborate on what jitter robustness means?
So remember, you're composing larger patterns from a composition of smaller patterns, right? And you're really interested in the physical arrangement of these sub patterns. Like a flower has got petals and sepals and all the rest of it. But if one of them wiggles a little bit, is the pattern destroyed? Not really, right? So if any subcomponent, you want to be able to say that if my petal is off by 1 pixel, it's still a flower.
Okay.
Right? So you want to allow each of the sub-patterns to have some ability to wiggle around and still detect the larger pattern.
And how do we achieve that? By having a stride of 1 with...
The stride of 1 is just mathematical convenience. The max is the key.
Oh, okay, I see.
Max is the key, right?
Okay,
yeah.
Does this help with scale variance as well?
Not quite. Yes, Lakshya.
So Professor, why can't you do min pooling also? Why only the rather than max pooling, you only pick up the minimum feature?
If you pick up the minimum, what does the min tell you? If you've got noise, if something is off by a little bit, you're forcing missing things rather than detecting things, right? Again, go back to the idea, right, of the big picture. How did we say there's a flower in this image? If you found a flower somewhere, you fired. So you picked the max. So this is just a very small scale version of exactly the same thing. If you pick the min, even when you have a flower, you're always going to say there's no flower, right? Yeah.
Input will be, when would you choose mean pooling over max pooling? Like what use case? How would you decide whether to go with max or mean?
It has to do a little bit. It gets into heuristics, but the real issue seems to be with training, as far as I can make out, in that we can talk about it when you talk about derivatives. As you pass derivatives backwards, if you perform max pooling, you're only passing derivatives to the location of the max. And in the early stages of training, that can be wrong. So you're going to accumulate the wrong derivatives. Yeah.
Even the learned filter, there's that's the filter anyway. Like pooling at that.
So you're right. So this thing is not really going to be very effective. You might just have as well replace it with a full convolutional layer. And so this is, but this has been tried. So pooling layers scan the input using a pooling operation, selecting the max from a k cross k block of input. Each pooling filter scans individual maps in the previous layer to produce an output map. And for pooling, we do not generally pad the edges. This is the summary, right? So the types of convolution operations we perform considered so far are convolution and pooling. There are 2 more operations that are kind of important. The first is downsampling, where you try to reduce the size of the input. And the way you go downsample is to just ignore things. So it's like saying, if I have this 128 cross 128 image, I want to reduce the size to 64 cross 64. You just ignore every second row and every second column. So that's like saying, I'm just blocking out all of these regions, which I don't want to consider. Just replace them with zeros and then compact it, right? So this is your downsampling layer. And so downsampling pseudocode, you just basically if S is the factor by which you want to downsample the input, you're basically reading every nth column and every nth row. Now, typically, if downsampling follows a convolution layer, this is the same as convolving, but with a stride of S. So instead of convolving and taking a stride of 1, if you convolve with a stride of S, this is identical to convolving it with a stride of 1 followed by a downsampling layer. Now, procedurally, you just take a stride of S. But conceptually, it's much more convenient to think of it as convolving with a stride of 1 and then downsampling by S. And that's going to help us during backpropagation, we will see, when we compute derivatives. So also for pooling, I can pool and then take a stride of 1 and then pool again. Or I can pool with a stride of S, which is what is normally done. But for mathematical purposes, for convenience, it's convenient to think of it as just pooling with a stride of 1 and then downsampling by S. So this is, here, for example, if I were downsampling by a factor of 2, here's how I'd be performing the computation. And obviously, this is going to result in a larger reduction in the size of the input. I'll skip that bit, okay? So if your stride is S, then the output is not going to be n minus m plus 1. You're going to be striding over the n minus m with the stride of S. So the output size is going to be n minus m over S plus 1, right? So the downsampling after pooling can be merged. So for example, if you are performing max pooling and then downsampling by 2, that's just like saying I'm going to be striding by 2 every time I perform the max. Now, same thing with mean, right? So typically, pooling layers are followed by downsampling. In fact, pooling is combined with downsampling. So you're going to have pooling with downsampling. And so, yeah.
Isn't pooling basically just downsampling taking the max value?
It's not downsampling. I can slide by 1, right?
But it's still becoming smaller. Right?
It's pooling with stride makes it smaller. You don't have to be. The max is just a nonlinear filter, right? And so I have various examples of how pooling followed by downsampling can be seen as pooling with a stride. Now, there's another kind of operation which is called upsampling. This is also very common, where you want to increase the size of the input. And so the way you would upsample is to simply say, I'm going to expand my image out and I'm going to introduce zeros. Easily done, right? So if I want to upsample by a factor of S, then I'm going to introduce S rows of zeros and S columns of zeros between every 2 rows and columns. And again, this is a very easy operation. This increases the size of the input. So typically, when you upsample, you don't upsample. Upsample is never followed by pooling. Because if you upsample followed by pooling, yeah.
Is there any equation to upsampling?
We'll encounter it, yes. Typically, when you actually, for example, if you are reconstructing images using any kind of autoencoder, you want to go down to, and then you're going to make in size and make it large again. We use it all over the place. So you never follow upsampling by pooling because you could just end up pooling a whole bunch of zeros. You lose a lot of information. So upsampling is almost always followed by a convolutional layer. And so here, upsampling, the code is very simple. You just introduce S minus 1 rows of zeros between every 2 rows and S minus 1 columns of zeros between every 2 columns. Now, upsampling followed by a convolutional layer is often viewed as convolving with a fractional stride. So if I'm upsampling by a factor of 2 and then following it by a convolutional layer, you will often hear this as being described as convolving with a stride of 0.5. That's because the size is increased, right? But that's just terminology. So map sizes can be changed by downsampling or upsampling. Downsampling, you drop S minus 1 of S rows or columns. And upsampling, you insert S minus 1 zeros between every 2 rows or columns. Downsampling typically follows pooling or convolution. Downsampling doesn't occur. Downsampling is going to be the final operation in a sequence of operations, which is why it can be merged and say it's this operation being done with a stride. Upsampling always precedes some other operation, because if upsampling were the final operation, you're going to be left with a bunch of zeros, which is not really conveying any information. Yeah.
During the upsampling, why don't we do things like linear interpolation?
You could, and it would actually be better than introducing zeros. But then you're assuming that the filter convolution filter figures out what to do. So the story so far, just adding to everything that we've seen so far, convolutional neural networks are supervised versions of the computational model of mammalian vision. It includes convolutional layers comprising learned filters that scan the outputs of the previous layer, and pooling layers that vote over groups of outputs from the convolution layer. Convolution can change the size of the output. This may be controlled via zero padding. And pooling layers may perform max, p norms, or even be learned. Resampling layers increase or decrease the size of the map. Downsampling can be merged with the preceding layer by making it the same operation with a stride greater than 1. And upsampling can be merged. Upsampling must be followed by convolution. So, support. Okay. I'm using Yash as my clock. Every time he shuts his laptop, you guys are out of time. Okay, there you go. All right. Does anybody on Zoom, want to answer the first question? On Zoom? Is there anybody on Zoom?
A and C.
A and C. What about you guys? What do you think? First one. And what about the second one? D. Okay, so upsampling by S introduces S-1 zeros between adjacent rows and columns, and it's generally followed by convolution. Downsampling by S deletes S-1 consecutive rows and columns, and they're usually merged with the convolution or pooling operation from the preceding them. So it's like performing that operation with a stride. So let's set everything together for a typical image classification task. I'm going to assume max pooling. Let's say I'm trying to build a classifier to detect houses and mountains or something, right? Your image, typical image, color image is not just one image. It's actually a stack of 3 images, R, G, and B. You can have other kinds. There are different ways of representing images, but then if you have color, you're always going to have multiple colors being visualized simultaneously. That's how you see color, right? So the input would be, if you had a grayscale image, it's going to be just one image. But if it's a color image, you're going to have RGB, which you can stack into a cube as before. And so the first thing you would have is going to have a bunch of K1 filters of some size. And each filter is going to scan the input. So how many output channels would you have now? K1, right? So you're going to end up with K1 output channels. And the filters are typically small. They're going to be 5 x 5, 3 x 3, small enough to detect the smallest patterns. And then you'll often run into this bizarre 1 x 1 filter. What is a 1 x 1 filter? So is it going to be exactly the same pixel?
It's either brightening or decreasing it.
What is it? This is the non-distributed scan. Remember, you were reading 1 pixel from all of them and then computing an output. Remember this from the last class. You could either look at a window or you could look at a single location. If you looked at a single location, you're computing an MLP over 1 pixel from all of the channels. That's just your non-distributed scan. Remind you? right? Put 2 and 2 together. And so that's a 1x1 filter. It's computing an MLP. It's computing a single perceptron over 1 pixel from all of the channels. This was your non-distributed scan. So the size of filters typically is going to be some power of 2 and we like to increase or decrease the number of filters by powers of 2 for computational convenience, among other things. So the parameters you'd want to choose are how many filters, what are the sizes of the filters, and what is the stride. So most often convolution is going to be performed with a stride of 1 unless you explicitly want the convolution to decrease the size of the output. You also want to decide if you want to zero pad the input or not. So again, this is a decision, design choice. And zero padding is kind of important if you want the output to have some kind of a proportional correspondence in size to the input. So for example, you detect something at some location in the final output. You want to be able to go back and say exactly where in the input that was found. Then if the size keeps changing, that becomes a problem. So you might want to zero pad. So you're going to get as many output maps as the number of filters. And within each filter, of course, this is just the map that we've seen earlier. You are computing an affine value, which is summing over all of the channels. And within each channel, you're looking at a weighted sum of all of the pixels, right? And then once you've computed the affine value at each position, you're going to apply an activation to the affine value. You're going to get as many output maps as filters. So the learnable parameters are going to be, if each filter is L cross L, so there are L squared parameters within each channel. You have 3 color channels, so you have 3L squared. And then you have 1 bias for every filter plus 1. And then you have K1 filters. So those are all the learnable parameters, right? And once you've computed these, the next operation might be pooling. So you're going to perform pooling on each of these channels individually. And there again, the design choices are what is the size of the pooling window and what is the stride. So, and the actual operation is going to be performed in this manner. You don't actually perform the pooling by simply directly picking the max. You find the location and read the value at the location. But the parameters to choose are the size of the pooling block and the pooling stride, and also the kind of pooling, max or mean or what have you. And the actual pooling is going to be performed in this manner. At each location, you're going to find the location within that pooling window where the maximum value has happened. And this information is going to be stored. So you will actually store the location, the indices of the maximum value. And the output is simply going to be the value of the previous map at that maximum location. So this is just picking the max, but you're doing it in a 2-step process where you're first retaining where the max was found, and then you're reading that value off. So that's going to give you a stack of channels again. And then at the next layer, so again, filters are also often called kernels, and the outputs of individual filters are called channels. So K1, K2, etc. channels. I've called them maps because that's what, or planes is what Fukushima called them. Maps is what they really are. Channels is a terminology that snuck upon us at some point, so we're going to have to use it. Now, and then for the next layer, you're going to have some bunch of filters again, each with their own dimension. And each of these filters is going to compute one output channel. So since the number of output channels depends on the number of filters, you can always vary the number of channels in each layer by simply changing the number of filters. So although the input has only 3 color channels, the first layer could have 128 planes, right? The next one could have 256. It just depends on the number of filters. And again, the parameters to choose are going to be the number of filters and the size of the filters. And so the total number of parameters here is if you have K2 input channels, then you have K2 times L3 squared plus 1. That's the number of parameters per filter. And you have K3 of these filters, right? So those many parameters from the next layer. And then again, on those, you would be performing some kind of pooling. So the choice is to make what kind of pooling, what is the size of the pooling window, what's the stride, and so on. And then finally, when you're done through all of your convolutions, you're going to flatten all of these outputs and you pass it through an MLP. So here, the decision is, what is the size of the MLP? That's the number of parameters you'd have to learn. So each convolution layer typically has a stride of 1, so it maintains the size of the image. Each convolution layer will typically increase the number of maps from the previous layer. And so increasing the number of maps reduces the amount of information lost by subsequent downsampling. Each pooling layer with stride D decreases the size of the maps by a factor D. So, and filters within a layer are all typically going to have the same size, but different layers can have filters of different sizes. So the various parameters we'd have to choose are the number of convolutional and downsampling layers within each layer, the number of filters, the size of the filter. If you have looking at pooling layers, the size of the pooling filter and the kind of pooling operation. Now there's one, okay, we'll finish this poll. Time's up, guys. Which is the answer?
They're the same.
They're the same, right? Okay, good. So there's one final thing that you have to think about. It's about information. Now, what is the amount of information that you have in an image? It's the number of pixels, right? So suppose I have 3 channels and 3 color channels, and I have a 128 cross 128 image, right? Or let's generalize. I'm going to spend a minute on this. If I have K1 of these guys, if I have K1 channels and I have cross, say, an L cross L or L cross width cross height output, the total number of values I'm going to get is going to be K1 cross times W times H, okay? So now I process this through some K2 filters. And then after I process through this through K2 filters, I do some pooling. Or maybe I just have convolution with stride, or I may have convolutional layer followed by a pooling and downsampling layer, okay? So if I follow this, what is the size of the output of each of these channels going to be? If I just have K2 filters. With padding, it's going to be the same thing, right? So you're still going to get about W times H times K2. So now you have K2 times W times H. And then I followed this by pooling and downsampling. And let's say my downsampling stride was 2. After downsampling, how many values will I have after pulling and downsampling?
H by 2, W by 2.
This is going to be K2 times W times H divided by 4. Correct? So under what conditions, what is the minimum condition I require to make sure I have not lost information? Yeah. You want K2 to be 4 times larger than K1. So every time you downsample, you're going to lose information, right? So you have to plan for downsampling by increasing the number of filters, which is why as you go through a network, you're going to find that the maps get smaller and smaller, but the number of maps keeps increasing because that's how you retain information. That makes sense? Yeah.
Do we always need to retain information?
Not necessarily, but if you want to, you do, right? Very often they're filtering, they're cleaning out stuff that you don't need. Yeah.
In downsampling, you lose layers and columns, but is there like a minimum size to which it's feasible to use a layer? Because you have a certain size that you start with, and every time you downsample, you shrink the.
Correct. Eventually, you can end up with 1 pixel.
It's like the smallest value.
Yeah, because beyond that, you're throwing everything away, right? Yeah.
So it mentioned that the size of all the filters should be seen.
Yeah, within a layer.
Yeah. So why can't we have a different filters in between?
You could. It's just going to be much more tedious to work with, right? Yeah.
You mentioned that we don't want to lose information, so we keep the number of neurons constant.
The total number of values computed.
Total number of values, yeah. Probably a dumb question, but when we are done with double convolution, the part of the network, aren't we going to lose information anyway when we pass it?
Yeah, but while you're performing stuff, you don't want to lose information early, right? Because this might be important. That's all. Yeah.
Do we have to consider aliasing when we're downsampling?
So from a signal processing perspective, yes. But again, you're increasing the number of channels. So eventually you're not. If you make sure that the number of channels is increased, then you can always deal with it. It's like a wavelet filter, right? You're looking at different things. You're downsampling each of those, but then you retain all the information. Yeah.
I'm curious, with increasing our K2 to be 4 times as K1, effectively, we still have the same number of parameters that we're holding on to. So why do we prefer to have larger number of layers and smaller, let's say, sizes of the values that we store versus like we're holding on to the same number of parameters?
So the point is when you actually compress the whole thing, then each of the planes is going to be a summary of the entire image. Whereas you're going to have position specificity otherwise. So you're trading off,
Okay.
Summarization, but you don't want to lose information. Okay, we're kind of done. I had some slides over here. Here was the entire digits classification framework that Jan LeCun had. The details are on the slides. One final bit, training. Training is just like in the case of a regular NLP. The only difference is in the structure of the network. At the output, you're going to provide images and labels, and you're going to perform backprop. Backprop is going to be, and all of these parameters would have to be learned. We're going to spend some time on training, right? You'd compute the divergence as before. You can compute the loss as before. And we need to be able to compute the derivative of the loss with respect to all the filter parameters. That's good. That's going to be the bugaboo out here, which is this term. You can compute the derivatives going back to the input of the MLP using the standard backpropagation rules. The real challenge is in how do you compute derivatives going further back? And this is what we're going to deal with in the next class. Please look at the slides. There's stuff on the slides that's going to come up in the quiz. I haven't been as clear today as I would have liked to be. I'm a bit under the weather, but still, that doesn't stop me from posing those things in the quiz.
I'm gonna go to a dark, but you guys can show me.